All right, thank you very much for the invitation to speak. I think last time I spoke here was when I was a grad student, maybe. I don't know, so it's fun to be back. Apologize for the date being wrong on there. Okay. All right, so let me start with some background. So this is a discussion of explicit class field theory. It's a very famous theorem of Kronecker and Weber, which says that the maximal abelian extension of Q is the cyclotomic extension. So you adjoin all the nth roots of unity for every integer n to the rationals. Then you take their union or composite m, it's the same thing. You get the field of the maximal Galois extension of Q that has abelian Galois groups. So it's a big infinite extension. And there's one other class of fields for which we can give a theorem like this, where we can write down explicitly what the maximal abelian extension is, and that comes from the theory of complex multiplication. So if I start with a quadratic imaginary field, so Q adjoin root negative d, where d is a positive integer, then the maximal abelian extension is given by, well, join the J invariant of an elliptic curve that has complex multiplication by the ring of integers of that quadratic imaginary field. And that generates the Hilbert class field of that ground field. And then to get the ray class fields of all conductors, you adjoin the torsion points, the coordinates of the torsion points, essentially, of this same elliptic curve. Now, it turns out that's not quite right. There's something called the Weber function, so I don't want to get into that's a technical thing, but it's basically just the coordinates of the torsion points. Okay. So in his ICM address, very famous in 1900, Hilbert stated a list of 23 problems. Right in the middle was the 12th problem, which says that, okay, so these are quotes translated from the German into English. The theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. So that's the first result I stated on the previous slide. And then the second result is kind of summarized in the second quote here. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So I think at this point in history, the previous theorem was not known in exactly that format. And in fact, it's a little bit of a mistake that people make. People think that Kronecker's Jugendtraum is the same as Hilbert's 12th problem. In fact, Kronecker's Jugendtraum is this. I think it's to solve the quadratic imaginary case. So that was solved. Then finally, so this is the focus of my talk, the extension of Kronecker's theorem to the case that, in place of the realm of rational numbers or the imaginary quadratic field, any algebraic field, whatever is laid down as realm of rationality, seems to me of the greatest importance, and I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So the case that I'm going to be focusing on today is when the ground field is a totally real field. So for example, a real quadratic field, Q adjoin root 2, Q adjoin root 5. Okay, so let me just give some historical background about the strategy that will method that I'm using, which is using L functions and more specifically Stark's conjectures. So Stark stated a series of conjectures proposing the existence of elements in Fn. I apologize, I haven't defined Fn. Fn is the ray class field of conductor n. So this you can just replace that Fn with Fab, maximal abelian extension. So proposing the existence of elements in abelian extensions of F whose absolute values are related to L functions of F. So we made a series of papers and advances in math from 71 to 80, which stated some conjectures in this direction. So Tate makes Stark's conjectures more precise in every case, and in a certain important case with a finite prime, which I'll be getting to later, and that'll be the focus of my talk, he stated what's now called the Brumer-Stark conjecture, though I like to call it the Tate Brumer-Stark conjecture, since Tate is the one who stated it. Gross refined the Brumer-Stark conjecture with a conjecture that I'll state later, using p-adic L functions. And there's been work in these directions. So Rubin and Popescu made the higher rank version of Stark's conjectures more precise. The naive generalization of Stark's conjecture to the higher rank case, which people assumed would be the natural higher rank generalization, turns out to be false. And Rubin stated what's actually the correct version. It's a little bit subtle, and I won't get into that today. And Popescu and Greither have some nice recent work where they proved a lot of the Brumer-Stark conjecture, but under some Iwasawa theoretic assumptions, such as the vanishing of the Iwasawa mu invariant. So And so I won't really get into that. So my work is kind of orthogonal with theirs in both the metaphorical and literal sense, as you'll see later. So let me talk about p-adic L functions. Even though this isn't the focus of the work, it is important background or historical background for what I'm going to be talking about later. So we'll start with a totally real field, and we let H be a CM field, which is an abelian extension of F. So it's not necessarily quadratic. It's not that F is necessarily the maximal totally real subfield of H. It's just a CM field that is an abelian extension of F. And I let chi be an odd character of the Galois group. So odd means that chi of the unique complex conjugation in H is -1. Then Deligne and Ribbett, and also Kasounogas independently at the same time, constructed a p-adic analytic function, which was called the p-adic L function, associated to, well, I'd like to say chi, but because of historical notational reasons, I'll have to say chi omega, where omega is the Teichmuller character. But this is just notation. So if you want to think of this as LP of chi, that's fine. So it's a p-adic L function associated to chi of a p-adic variable S, which has the property that its special values for non-positive integers agrees with that of the classical L function, as long as you remove the Euler factors at p, which is what that star denotes. Okay? So it turns out these are algebraic numbers, so as long as you fix an embedding of q bar into Cp and into C, then you can make sense of this statement. You can compare these two kinds of numbers. So since these kinds of integers, non-positive integers that are 0 mod p minus 1, are dense in Zp, this function, if it exists, then by being continuous would be unique. So the fact that it exists is the content of the theorem. Okay. So I guess, okay, technically, if chi is omega inverse, then this is just the p-adic zeta function, and this has a pole at s equals 1, but that's sort of the only bad case where there's a pole. Actually, it's a big conjecture that there's a pole. It's equivalent to Leopold's conjecture that the p-adic zeta function has a pole at s equals 1. Okay. So now Gross's conjecture is a study of this p-adic L function at s equals 0. That's a very natural question to ask. What is the order of vanishing, and what is the leading term? So this is a generalization of Stark's conjecture, which in turn is a generalization of the Dirichlet class number formula, the class number formula for the zeta function of a number field. You can state it at either s equals 1 or s equals 0, and you can ask what is the order of vanishing there and what is the leading term. So that's what Gross did. He studied this, and he conjectured that the order of vanishing of the p-adic L function at s equals 0 is given by the number of primes above p in your number field such that chi of p is 1. Okay, so the number of primes that split completely in the fixed field of chi that lie above your prime p. And this has to do with the idea, well, I'll explain the idea in a second, but this has to do with the Euler factors above p that vanish, and that passing from L to L star, you remove the Euler factors at p, and this is the number of such factors that vanish at s equals 0. So furthermore, he conjectured what is the leading term of this p-adic L function at that point. So you take the rth derivative, and in the usual way you divide by r factorial, and then you scale it by a certain non-zero algebraic number, which is the value of the classical L function associated to that chi. This is a non-zero algebraic number because chi was odd. Okay? And we have explicit formulas for this L also. Then the conjecture is once you normalize it in this way by this explicit algebraic number, then what you get is a p-adic regulator, okay, times the other Euler factors that you remove that aren't vanishing. So as I mentioned, this R, the number of primes such that chi of p is 1, that's the number of Euler factors that vanish at s equals 0. These are the Euler factors that don't vanish. So once you divide this out, then what you're left with is just a p-adic regulator. Okay, so this is a certain, so I'll actually state what this is, this Rp of chi. I'll state what it is precisely later. But let me just say that it's a determinant, I'll say now, it's an R by R determinant of p-adic logs of units. Okay, so it's just like what it shows up in the Dirichlet class number formula. You have a matrix of logs of units, and you take the determinant. Okay, but everything's p-adic now, so it's p-adic logs, and the units are p units. Okay, so what's known about this conjecture? So about the order of vanishing, we know that the order of vanishing at s equals 0 of this p-adic L function is at least what's expected to be the order of vanishing. It vanishes to order at least r. Okay, so this is non-trivial, even though the intuition is clear that it's the number of Euler factors that vanish. So it's saying you're multiplying r numbers together that are each 0, so you should have order of vanishing r. The point is, if you remove even one of those factors, what's left is no longer analytic. So you're not multiplying together r analytic things that each vanish, so therefore the order is at least r. It's not that trivial. So the original proof that was given was built on the key thing that went into it was Wiles' proof that Iwasawa made in conjecture. Wiles proved that this analytically defined p-adic L function was equal to some algebraically defined p-adic L function, which you could then identify that the order of vanishing was at least equal to r explicitly, and therefore you would get the result. Now, one thing I can say is that there are apparently issues for p equals 2 for this, oops, wrong button, for p equals 2 for that proof, which I was unaware of until this paper that I'm going to discuss next was refereed, and they pointed out actually this is a new result for p equals 2, which is that later, together with Charlois and separate work of Spies, we proved using the Eisenstein Cocycle that this order of vanishing is at least equal to the expected one, and the proof is totally different from Wiles. So we don't make any connection to the algebraic p-adic L function. We analytically study this p-adic L function, which is analytically defined in terms of the Eisenstein Cocycle, and we just calculate the first r derivatives and show that there's 0. Okay, and p equals 2 is no special case. So it's a very different proof than Wiles. Okay, so that's the order of vanishing. And then more recently, in separate work with Mahesh Kakde and Kevin Vintullo, we proved the leading term formula in Gross's conjecture. So this is just repeating what I wrote in earlier. The rth derivative, scaled out in this particular way, is equal to this Gross regulator, which is an r by r determinant of p-adic logarithms of p units in h in the extension up by chi. So these p units are called Brumer-Gross-Stark units. I mean, they're either called Brumer-Stark units or Gross-Stark units, depending on whether people care about this conjecture or Brumer's conjecture, which I'll state later in the talk. Okay, so these units I'll define, and these units are going to play an important role in this talk. But let me just, for a moment, just talk about the proof a little bit in a very vague way. And these ingredients will go into the methods that I'm going to talk about in more detail for the question that I actually care about later in the talk. So this will be a good introduction to that. So the first step in the proof is to reinterpret the relevant unit group in terms of p-adic Galois cohomology. This is basically just Kummer theory. Just one usually does the connection between the Mordell-Weil group of an elliptic curve and the Selmer group. In this case, we know that that map is an isomorphism because the obstruction, which in the elliptic curve case is the SHA, we know in the unit case is just the class group is finite. So we actually get an isomorphism there. So we can reinterpret the unit group in terms of p-adic Galois cohomology. And then so that gets us to the problem of constructing certain Galois cohomology classes, and those are constructed using Ribot's method, which I hear that there is a grad student seminar on. So hopefully people are familiar with Ribot's method in this audience now. And so the format of it that we use, as in Iwasawa theory, we use p-adic families of Hilbert modular forms, and the connection between L functions and modular forms is that Eisenstein series have L functions as constant terms. Then we use the Galois representations associated to, well, cuspidal, not really modular forms, but cuspidal forms. So we get some congruence between the Eisenstein series and a cusp form using the vanishing of the L function, because that's the constant term. And then using the Galois representations associated to these cusp forms, we get the necessary Galois cohomology classes. And then bringing the whole thing full circle, you show that the cohomology classes that you construct satisfy the necessary formula via their explicit construction with the Eisenstein series, that the L functions sort of show up in a way that relate them to the invariants that give you the p-adic logarithms of the units.
So you actually construct the units?
No.
You construct something like the space they span?
It's not even that. We construct... Not even that. We construct something orthogonal to the p-adic space they span. So it's like there's a line that the units are lying on, and I don't see the units on the line. There's some z lattice inside this QP line, right? And then I construct a line that's orthogonal, and I calculate its slope. and I say, well, this thing's orthogonal, so its slope is -1 over that.
But these lines are subspaces in your situation.
Yeah, they're subspaces of some ambient two-dimensional space, and the units are sitting in some line in there.
But it's not more than two-dimensional in the R by R case?
Yes, it is. Now you're getting into technical. Yes. No, that's exactly right. That's what we had to get around. That was one of the main kind of psychological things we had to get around in the R by R case, is how to deal with this higher dimensional thing. Yeah. So in the rank 1 case, it's two-dimensional. Exactly right. All right. So all right. So previous work that served as background for this are the Ribot's method, of course, and then as used by Mason and Wiles in their proof of Iwasawa main conjecture, and then something that's slightly different is Greenberg-Stevens, where he related the derivative of the UP operator to these L invariants, and that's kind of something that shows up in an important way in our work, the derivative of the UP operator. So I should mention there's a particularly delicate case, and in particular what Akshay mentioned, when you have an R by R determinant, that's something that you usually don't see in these other methods. So some new ideas that have to go into that. I probably won't get into that today. Okay, so let me get more towards the topic I want to talk about, which is Hilbert's 12th problem, what I motivated this lecture with. So let's talk about Brumer-Stark units, or Brumer-Gross-Stark units. So let's say we have a finite prime that splits completely in this extension H, and we fix a prime of that field above P. And this T that I have to introduce is just a technical thing to make everything correct. So the group of units that we care about is a group of P units. So they're units except for at primes above P, okay? And this includes, these W's include complex places. So I'm saying they have complex absolute value 1 at all the complex places, okay? And then there's an additional assumption they have to be congruent to 1 modulo all the primes above those in the set T. So by the way, I should mention this fact that they have complex absolute value 1 at every complex place has been kind of attractive to a lot of people because these are Weil numbers. So it'd be really nice if we could identify these numbers as the eigenvalues of Frobenius on the cohomology of some variety, because they should, because they have complex absolute value the same at every complex place. And in fact, this was done over Q, when the ground field is Q, by Katz, who found a p-adic formula for Gauss sums by relating that, by showing that they're eigenvalues of Frobenius on the Fermat curve or certain Artin-Schreier curves, and then having a really clever method by some iteration process to give a p-adic formula for those, and that was then interpreted by Gross and Koblitz to relate that to the p-adic gamma function, which then, via the work of Ferrero and Washington, was related, or was it Greenberg or Greenberg? Now I'm getting confused. So anyway, someone related that p-adic gamma function to the p-adic L function. So that actually gave a proof of the Gross-Stark conjecture that I stated earlier in the case of the ground field is Q, with this idea of showing, using the fact that these are Weil numbers. But nobody's ever been able to do that method when the ground field isn't Q, because we don't know what are the varieties we want to write down to identify these units as eigenvalues of Frobenius. Anyways, so there's this unit group, and so I guess I'm going to state it in kind of a funny way, but I'm going to state it as a lemma first, that there exists a unique element in this unit group tensored with Q such that the p-adic valuations of all the conjugates of this unit, if you twist them up, if you project them onto the chi component, gives you the L function of that chi for every chi. Okay, so if you unwind this, this basically says that the p-adic valuation of sigma of u is just the partial zeta function associated to that sigma. Okay, but then smoothed in this way with this set T. Okay, and then the conjecture of the Brumer-Stark conjecture, which was stated by Tate, was that this element is actually an honest-to-goodness unit and not just something in U tensor Q. Okay, so the reason I state it this way is I want to speak about this element U unconditionally in the future. So when I speak about it unconditionally, we think of it as an element of U tensor Q. When I have to make it, when I speak about Brumer's conjecture, then it's actually a unit. Okay. So Gross's regulator is just the determinant you get by taking the p-adic logarithms of the norms of these units. So there's one unit for every p. So I have these r primes p. These are the r primes p that says that chi of p is 1. So I have r primes p, and then I can take the p-adic log at each of those r places. So that's r rows and r columns you can have. And then you take the determinant, and you normalize the denominator. This is just some algebraic number in a certain way. So by the way, for those who are more familiar with, say, elliptic curves and the p-adic uniformization of elliptic curves, this looks very much like an L invariant. It's a log p of something over the ord p. That's really what it is. It's a form of L invariant. There's a general framework for L invariants in which that L invariant and this one appear defined in the same way. So it's not a coincidence. That's due to Greenberg. OK, so to put this in words, this regulator that I just defined, it's a determinant of the p-adic logarithms of the local norms of the Brumer-Stark units, UP. Now these Brumer-Stark units, okay, they're uniquely well defined. So they're uniquely well defined in U tensor Q, and they're conjectured to lie in U, but they're unique. But Gross's conjecture gloms them together in some complicated way. Right? First of all, you're taking the norm. That's, to me, the most important part. You're taking a local norm, so you're kind of losing a lot of information. So for example, if you take a local norm from C to R, you take the absolute value, basically, squared. And so that loses all the information about the argument. So you can't reconstruct the unit from the argument. And this was actually, I did my senior thesis in college on Stark's conjectures. I thought about the Archimedean ones, and I tried to write down explicit Stark's conjectures, and I thought I could just willy-nilly manipulate the conjectures to write down the unit. And I got really annoyed when I realized that I was trying to write down complex numbers, and all Stark's conjecture gave me was the absolute value, and I couldn't produce the actual number from it. So I couldn't write down its minimal polynomial without a lot of extra work beyond just using the conjecture. So the question is, can you write down a formula for the unit rather than just for its absolute value? And then in Gross's conjectures, they're glommed together in an even more way, which is that you have to take these logs and sum the twisted characters, and then you take a determinant, which who knows what the heck that does. We don't even know if that vanishes or not. Okay, it's supposed to, conjecturally doesn't vanish, but we don't know that. Okay, so that was actually a question because I got so annoyed about it in my undergraduate thesis that I turned into my PhD thesis, was to write down a conjectural exact formula for these units. Okay, and I did it in kind of a maybe a cute way with modular forms over real quadratic fields in my thesis, but there's a much more general and kind of conceptually more pleasing way using what's now referred to as the Eisenstein Cocycle. So let me talk a little bit about the Eisenstein Cocycle. Okay, so maybe we'll collect ourselves here, and I will recall the setting a little bit. Okay, so H is a CM abelian extension of a totally real field F. Now I have a prime P of F, which a finite prime, which splits completely in H. And let me, for simplicity in this discussion now, assume that H is the maximal such field, maximal such CM abelian extension of F, of conductor, this integral ideal F, in which P splits. Okay. So associated to this setting, there's something called an Eisenstein cocycle, which is a cohomology class, a group cohomology class in H. D, so D is the dimension of F over Q, okay, the degree of F. So there's a cocycle in H D minus 1 of F star acting on measures on Fp. So this is just the completion of F at P, which you can think of as the product of the completions of F at all primes above P. And this has a rich history, has been studied in dozens of works. So maybe just now I'll mention the work of Solomon, Hugh, and Hill on Shintani's method. And then that was built on work myself with Charlois and Greenberg, and also Spies and others. But there are other constructions that don't use Shintani's method. So Siegel never mentioned a cocycle, but if you look at Siegel's formulas for special values of L functions, you can view them in terms of integrating Eisenstein series in the upper half plane. You can view this as a form of the Eisenstein cocycle. And this method of Siegel is recently, I guess in current work, being generalized by Bergeron, Charlois, Garcia, and Venkatesh. Do you guys have a preprint yet? You're not even sure what you've done. Well, okay. Well, when I talked to Nicolas, basically it generalized this from Siegel's work and the upper half plane for GL2 to sort of Eisenstein series for GLN, and integrating them, and you can get a cocycle that spits out values of L functions. So there are other methods due to Stevens, Check with an incredibly beautiful method using conditional convergence, and more conceptual methods due to Norrie and King's, Valence, and Levin. So there's a lot of work and lots of methods to apply this, but they're all different avatars of the same basic concept, and they all go by the name of the Eisenstein Cocycle.
But usually you construct it in GLD.
Yes. So I'm choosing an embed, like an isomorphism as Q vector spaces of f and q to the n. So then you can q to the d. Sorry. So then you can embed f star in GLD. So yeah, the more general construction is hd minus 1 of GLD of q, and then I'm embedding f. So I'm taking a restriction. Okay. And so you might have it valued on zp to the d, and then okay, that same isomorphism, or qp to the d, and then same isomorphism gives me an isomorphism, makes me view that as measures on fp. Yeah. So I'm restricting. Okay, now associated to each p is a certain cohomology class due to space called C construction. Actually, I'm not going to get into the definition of that. Let me just move ahead. And then the last bit of input into this conjecture is just the generator of this group of units. So f is totally refilled of degree d, so its unit group has rank d minus 1. And then if I invert 1 prime p, then the unit group is rank d, so it's h. And this should be a subscript of a plus here. So I take totally positive elements. So then it's just a free abelian group of rank d. So it's h lower d is one-dimensional, it's z. So I take a generator, and there's a way to choose the sign of the correct generator. And then the conjecture is that the Brumer-Stark unit is just given by the cap product. So you take this class in h lower d, and you cap it with this class in h upper d minus 1, so you get something in h lower 1, and you cap it with this thing in h upper 1, you get something in h lower 0, which h lower 0 of f, acting on fp star, and it turns out to just give you an element of fp star. And the formula and the conjecture is that it's the Brumer-Stark unit. So I don't have time to go into details of what this is exactly and what the Eisenstein cocycle is. I've given entire lectures just explaining this conjecture. I don't know if I say something more, but let me just say that it is concrete. So if p, let's say, is just generated by a rational prime p for simplicity, then what that says, if you unwind it, what's the pairing between functions and measures is you integrate them. That's how you produce numbers. So it says that a certain p-adic integral, which you can write down explicitly, is my unit, okay, and the power of p is some certain L function. And this conjecture actually more specifically gives a conjecture for all the conjugates, not just for that one p. And so this is maybe the highlight of the talk. So Akshay says any good number theory talk has to have a number. So there's a number 305. Okay. So this is so these are computational examples that actually were done on a computer. So you take f adjoins square root of 305, and I want to take the narrow Hilbert class field, and I want to take a small prime p. So I took p equals 3. So you can check 3 is inert in there. And so you compute all the conjugates. So you calculate that integral up to like 50, or I think it was maybe even more in this case, 100 p-adic digits. And you calculate the elementary symmetric polynomials, and you ask Perry, like, is this close to an integer over 2 plus another integer over 2 times square root of d? And Perry tells you, yeah, 9 and 3, 4. And you have like something like that's 100 p-adic digits long, and then it turns out to be 9 halves. Then it's a pretty good chance that it wasn't garbage and it was 9 halves. Right? So then you write down this polynomial, and then after the fact, you can check, hey, what's the splitting field of this polynomial? And beautifully enough, it is the narrow Hilbert class field of f. So this is an honest-to-goodness computational way of computing Hilbert class fields.
How long did this computation take?
That's a good question. I mean, it's certainly less than a day, and it depends how many digits you want. So there's a certain amount of preloaded thing, like basically, like I think you run one program for a day and it calculates a bunch of integrals, and then for every real quadratic field, you then get all the polynomials quickly.
So what's the biggest case?
I don't remember the biggest case, but here's a bigger case. So this is a degree 6 case I did. So f is q adjoint root 473. So I wanted to always do the Hilbert class field and still have a big degree and still have p. Anyways. So this weight 473. And so d, by the way, is this 473. And then you do it. And again, like this might look like a big number, but it's way less than 5 to the 100 or so. So these are almost certainly right. And if you actually check, and I did this, actually maybe I just asked Perry to do it, but you check that if you take the splitting field as polynomial, you get the Hilbert class field. All right, so this is an honest to goodness way. And let's go back to Hilbert's 12th problem. What can you actually say theoretically about whether this solves Hilbert's 12th problem? You can show that these units, actually generate the maximal, this field that I mentioned, the maximal CM subfield of the conductor F in which P splits completely. Which means, well, there's always some prime that, in any extension, there's always some prime that splits completely. Chebyshev density theorem. So it follows that if you take all the units over all possible conductors and all possible P's, that you basically get the compositum of all abelian CM extensions of your ground field. And therefore, if you throw in some appropriate square roots, then you actually get the maximal abelian extension. So basically, these elements that we're writing down explicit formulas for, conjecturally so far, together with some explicit other elements you can write down very easily, some just square roots of elements in your ground field, that generates the maximal abelian extension, which is what Hilbert wanted you to do, is give a p-adic analytic formula for these elements. So this conjecture, if you can prove it, both theoretically and practically, would solve Hilbert's 12th problem. So the punchline is it's still work in progress, is that we're trying to prove this conjecture. And the method of proving this conjecture is to apply the methods that I described earlier with Cockday and Ventullo for the p-adic L function in this, to this conjecture. And I'll say a little bit about how that works. How am I doing on time? Unfortunately, Ventullo is now working at Facebook, so Mahesh and I are left to work on this on our own. But we're trying to apply the methods of that proof to prove this conjectural formula. So let me just mention some new features. So first of all, the Gross-Stark conjecture that I mentioned in terms of the leading term of the p-adic L function, it has an integral refinement that I'm going to state later that's due to Gross. And there's a higher rank version due to Popescu. So I won't state that one today, I don't think. But that plays an important role in this work. So there's a method in Galois deformation theory called the Taylor-Wiles method. And one aspect of that Taylor-Wiles method is to introduce auxiliary primes that are, primes L that are congruent to 1 mod higher and higher powers of P. And so that's a trick that's very important, and that's often called horizontal Iwasawa theory. So in Iwasawa theory, take sort of one ZP extension, and here we don't have one extension whose Galois group is ZP, but for a real quadratic field, say, but we do have bigger and bigger extensions whose Galois groups are Z mod P to the M. Chris, you seem...
Well, Wiles was doing this in his deal with the exceptional zeros.
Yes, so this predates Taylor. This idea certainly predates the Taylor, yes. But it was used in the Taylor-Wiles method, yeah. The idea is due to Wiles, absolutely. Yeah. And so the role of the p-adic Heda families of modular forms is actually something far simpler. It's just modular forms with coefficients in a group ring such that under every character of that group ring, you get a modular form of that Nebin type, which we call group ring valued modular forms. And again, this is not an idea that's due to us. I mean, somehow it's maybe in the exact way that we use it is, but it certainly goes back to Wiles, and that same paper, he has the same concept. So I want to mention something else before I go on in that direction, which is that I have a conjecture with Spiess, which is a different refinement of the Gross-Stark conjecture in another direction, which is this matrix that I wrote down, this R by R matrix, the regulator. Gross's conjecture tells you that its determinant is supposed to be the leading term of the L function. And what we found with Spiess is that the Eisenstein Cocycle tells you more than just the L function. You can write down a conjectural formula for all the principal minors of that matrix. So principal minor means you take a certain subset of the rows and you take the same subset of the columns. That's what makes it a principal minor. You take the same subset of the columns and you intersect them and you get a smaller matrix and you take its determinant. So for example, just the diagonal entries themselves are considered principal minors. So the 1-by-1 principal minors. And we obtain a formula for those. So this is another refinement, and so this would be sort of another work. So what it should give you a proof. If you could prove the higher rank version of Gross's conjecture, which I haven't stated yet, the integral conjecture, which is due to Popescu, then that should give you a formula for the principal minor. Prove our formula for the principal minors. It's another refinement. The application of what I want to talk about next. Okay. So now I want to set up the integral version of Gross's conjecture. So Gross's conjecture before was the leading term of the p-adic L function. This is very closely related conjecture, but it doesn't use anything p-adic. Okay, it's purely just classical L functions. So the setting is I have a totally real field F. I have a CM, abelian extension of F, which I call H. So it's the same settings before, and I let G be the Galois group. Now I let R be a set of primes above, containing those above infinity and those ramifying in H. And then S is R union this one extra prime P that splits completely in H. Okay, there's a finite prime P and it splits completely in H. And then for technical reasons, you have to have this smoothing set of primes T, which should be disjoint from your S. So Deligne, Ribbit, and Cassionogas, as I mentioned, so in this theorem about the p-adic L function, they also proved, using the same methods, that there exists a unique element in the integral group ring, which is kind of an L function evaluator. So if I take chi of this element, right, so for any character chi of G, I can apply chi to a group ring element, then that gives you the L function of your character chi with this kind of Euler-like product extract at the primes and T. So the Euler product at 0, the Euler factor would really be 1 minus chi of L. So that's why I say Euler-like. It's something that's a little bit strange. It's 1 minus chi of L times the norm of L.
What is L sub R?
Sorry. L sub R means remove all Euler factors at primes in R. So if this is minimal, then this is just L. So if R is literally equal to this set, that's just L of chi. Okay? It's just you have the choice of throwing in some primes. So I should have just done that, so I wouldn't have notation. But you have a choice. You can expand R if you want. And then you remove Euler factors at those primes. The reason it's going to be important is that there's going to be an L sub S, which is the same thing where you remove the Euler factors at S. Okay. Okay, so the theorem is that this element is integral. Like if this was C bracket G, then there would be no theorem because you can specify these chi of something to be anything you want on this side, and then you would get a unique element in C bracket G satisfying that. Okay, this C bracket G breaks up into a product over all the characters of C. Okay, but the theorem is that it's actually in Z bracket G. Okay, so you can state the Brumer-Stark conjecture in this notation, which is you fix a prime above P in your field, which is a capital Gothic P, and so you define ord sub G of a unit to be, well, you take the valuation of all the conjugates, and that's the coefficient of corresponding grouping element. And the Brumer-Stark conjecture is just that there exists a unit in this unit group that I described earlier, absolute value 1 at all places not above P, whose valuations are given by this theta element, the Stickelberger element. Okay, that was the Brumer-Stark conjecture that I stated. So I'm stating it in this integral group ring notation. But this is the exact same conjecture that I stated earlier. Okay, and now that I have that conjecture stated, I can state Gross's conjecture, if this thing would advance. Okay, which is, recall we had this finite abelian extension H, finite abelian extension of F containing H, and I should have written additional assumption here, which is very important, which I haven't written, that it should be unramified outside S. So this is the difference. H is only ramified at R, but then L is allowed to be ramified at P also, and P split completely in H. right? So S was R union P, which the P was this prime that split completely in H. But then now I'm allowing L to ramify, P to ramify in L, excuse me. So now you need some more notation, which is script G is the Galois group of L over F. So maybe, since the slides will advance, it'll be convenient if I draw some words. So I have L, I have H, and I have F. This is G, this is gamma, and this is, you know, and so by Galois theory, G implies gamma. Okay, so that's my setup. Okay, and I is what's called the relative augmentation. So of course, there's a natural map from script G to normal G, and that is called the augmentation. And I say, note that if I take theta sub S associated to L over F, that lies in the augmentation, because the reduction of theta st modulo I, I'll say this, I can write this down, theta st L over F mod I. So that's in Z bracket G. This G, that is just by functoriality of L function. That's theta st of H over F. And that's 0 since P and S splits completely in H. So the Euler factors at P for all the characters are 0. It's 1 minus chi of P. So there's 0. So that means that the projection of this under every character is 0, which means that it's 0. Okay. So that means that theta mod I is 0. So that means that theta lives in I. So this theta S lives in I. Okay. And Gross's conjecture is somehow, let me jump to the bottom, is to give you what's called the leading term of this theta. Once we know it's an I, then the natural thing is to look on in I mod I squared. So that's an idea that came from the Mazur-Tate conjectures in the seminar they were having at Harvard back when Gross was thinking about this, I think in 1980 or the early 80s. And the idea was, what should be the leading term of theta? That is, what is it? How do you even interpret that? It's just, what's the image of theta in I mod I squared? And the conjecture is that's given by the image of your unit here under the Artin reciprocity map. So if you take so there's a natural reciprocity map from class field theory, which gives me an element in the local completion of this prime of P to an element of this Galois group. So if I take that minus 1, right, so that's an element of gamma. If I take gamma any element of gamma minus 1, that's in the kernel, right? So if gamma is in gamma, then just the group ring element minus 1 is in I, because that's the kernel of modding out by gamma. So right, so modding out by gamma, then of course that goes to 0. So this element here is also in I, and its element in I mod I squared doesn't depend on what lifts I take of sigma. So this sigma tilde I haven't written down is just any arbitrary lift to script G. Okay, so its image doesn't matter what lift I take. So that's called, I'll call that rest sub G. And the conjecture is that the image of this Brumer-Stark unit under the Artin reciprocity map is this theta. Okay. Yeah.
So what does UP see the extension L at all? I mean,
no, it doesn't. UP doesn't. Yeah. Well, right. So, yeah, exactly. So somehow this unit here says that for any abelian extension of F that contains H that's unramified outside S, its image on the reciprocity map is related to this. Yep, that's exactly right. It doesn't see L. Okay. Okay. So now so the methods that I have, as Akshay alluded to earlier, say nothing about this Brumer-Stark conjecture. I can never construct a unit. Okay. So I want to make a conjecture that state a version of this conjecture that doesn't require knowing the Brumer-Stark conjecture. So if I go back, Gross conjecture starts with assume the Brumer-Stark conjecture, that is the unit that says, satisfies this, then it satisfies this. But I want to make a conjecture that doesn't require knowing that. So our conjecture is, forget any special unit. For all units, the or g times the theta s is the rest g times the theta r in I mod I square. So this is a conjecture that we stated, which follows from the Brumer-Stark conjecture, but it's weaker. I mean, for the Brumer-Stark unit, this is supposed to equal this, and this is supposed to equal this. Okay? So we're stating, what we're going to prove is something different, which is that for any unit, you have this congruence in I mod I square. Okay, and then that can be an unconditional statement. That doesn't require knowing anything else. Okay? Okay, and this weak, so the theorem is that this weak form of Gross's tower fields conjecture for all sets S and for all extensions L that I want to take. So now I remember why I needed to take arbitrary sets R to address your question before, is this is where we throw in the Taylor-Wiles primes. We throw in the primes that are highly congruent to 1 mod P, and this is the trick that we use, which is that if you allow yourself to throw in these other primes for your set S and you prove the conjecture in that context, and then you take the maximal abelian extensions L that are unramified outside those sets, then if you package that together for all possibilities, then that implies my conjectural exact formula with Spies using the Eisenstein cocycle for this unit and all of its conjugates. Okay? So this is a little bit hard for me to really explain the proof because I didn't really give you my formula. I didn't explain this Eisenstein cocycle business, right? There's a lot of mathematics there that I just hand-waved through. But let me just give you a flavor of how the proof works, which is you would join a prime to S whose norm is 1 mod a high power of P. Then Gross's...
Sorry, that prime, like in Taylor-Wiles, you have to choose the Frobenius, that's a very simple local definition. You're not doing anything like that. Just pick any prime with norm Q congruent to 1 and maybe that unit condition that comes a bit later.
This unit condition that comes later, that's important, yes. And you can accomplish this unit condition using Chebartov. Honestly, for me to know how to get this unit condition that I'm going to mention in a second, I need to apply more than 1 prime possibly. So this could actually be throw a bunch of primes. But for the slide, purpose of the slide, I just put 1 prime. Okay. So to get to address Chris's question earlier, so yeah, UP doesn't depend on L. So even though I've thrown in this extra prime like in S and I have a bigger extension L, what Gross's conjecture tells me is that the local component, if you look in the adelic description of the Galois group of L over F, that somehow it has a 1 in all the places outside of P. So yeah, if I had more than 1 prime Q, it would be U 1 1 1 1 1, right? In the product of the local completions of the ring of integers of F at those primes, modulo by the topological closure of the global units, right? That's how class field theory works. And the usual problem is that this OF star hat is eating up a big chunk of this. But the point is you can cleverly choose your primes Q such that the map U goes to U comma 1. The kernel of that map is contained in things that are congruent to 1 mod P to the M. So basically, if there's a cyclic quotient of this of size P to the M, which there is because of your choice of norm of Q, then that can take up this unit. So the set of things that have component 1 in the second component only are things that are congruent to 1 mod P to the M. And you can prove using Chebartov that you can choose these primes. So you might need to choose a bunch of them, but you can do that. So then this is the finally show that. This is actually, so this is the part where you need to actually show that you need to have your conjecture enter somehow, which is that you need to show that your conjecture, comma 1, agrees with the formula of Gross's conjecture. And that's in some sense a compatibility check of your conjecture. You can state our Eisenstein cocycle conjecture for any set of primes S, and as long as it's self-consistent, that when I add a prime S, I get the same, like one conjecture reduces to the other, then that will have this property. So.
Actually, Chebartov's proof of his density theorem uses adjoining auxiliary primes at this point.
Okay. I'll believe that. Okay. Good. All right, so that's the idea. So I just want to state that because that's a flavor. And I mentioned my conjectures with Spies on the principal minor of Gross's regulator matrix. So I'll say that now that there's a higher rank version of Gross's tower of fields conjecture due to Popescu, and a theorem that I stated, which is analogous to the theorem on the order of vanishing of p-adic L functions, is that in the rank R setting, theta is in I to the R. In the rank R case, it's not just an I, but it's an I to the R. And the proof, right, isn't as trivial as this proof, right? It's so this uses the Eisenstein Cocycle. And this should not be a theorem. This is like theorem star. We haven't proven this, but my guess, so this really shouldn't say theorem, but my guess is that this is true, that the higher rank version of Gross's Taylor-Felix conjecture should imply our conjectural exact formula. So this is why I stated earlier that I believe that if we can do what we're trying to do in the higher rank case, it should give our conjectural exact formula. Because as I said, it again boils down to this consistency statement for your conjecture, and the statement is so sort of canonical that it should satisfy that. But there are a lot of details to check in proving this theorem, which we haven't done yet. Okay. So let me just, so I only have a few minutes left, and in the last, I have 3 slides left. I'm just going to give a quick sketch on some of the aspects of the ingredients that we're going to use to try to prove this integral Gross-Stark conjecture. So I guess we're going to try to set up something for tomorrow morning where I'm going to give the details of how this proof works. So people who want to see Ribot's method used in current work, you can come tomorrow. I don't know. We'll try to figure that out. But so the group ring modular forms that show up, so these play the role of Hita families, and my previous work are, so they're just Hilbert modular forms. I guess they should say level. People usually say not conductor. Of level F and weight K with Fourier coefficients in the group ring such that for every element in this is the narrow array class group of conductor F, that the diamond operator associated to that ideal acting on F acts by just multiplication by this element. So another way of thinking of it is forms with coefficients in this group ring such that when you apply a character chi of G, you get a form with Neven type chi. Okay? So you can view them as families. Families where the thing that's varying is the Neven type. So families of forms with varying Neven type that satisfy congruences. So I notice that I'm fixing the weight there. So it's a little bit different than how people usually think about p-adic families of modular forms. These are purely classical in a sense. There's nothing really p-adic about it other than sort of only caring what's going on at p. So the coefficients are in ZP, but they're classical forms. Okay, so G is a quotient of GF, right? So G is the Galois group of some extension of conductor F. So it's canonically a quotient of GF. And so I have this tautological character of GF valued in the group ring of G. Then there is an Eisenstein series whose constant term is the theta element that you care about. Okay? So because of this smoothing at t, you have to have this weird factor. And because I want to make it integral, I clear the denominator of 2 to the d that usually is in the denominator here. But this is just the usual Eisenstein series. Okay? E1 of 1 chi. Okay, and so similarly, you have an Eisenstein series for the, so this is sort of the Eisenstein, so chi is varying over characters of this group, okay? And that's why I have theta r, because I don't need to remove the, right? So p is not ramified here, so I can have theta r. But then when I go to this extension, so by the way, for the simplicity here, I've assumed that this g factors as a product of my g and my gamma. Then I have E of 1 comma chi psi. And that is going to have constant term theta s, because this L is ramified at s. So this is how Ribot's method work, is you write down Eisenstein series whose constant terms are the L values that you care about. So the L values in this manifestation are these Stickelberger elements. Okay, so for a large positive integer k, we define, okay, so this is getting very technical, but that's good because we're at the end of the talk, basically. This linear combination of products of Eisenstein series. So basically, I want to do something, so I want to do something that looks like a cusp form, but is congruent to these Eisenstein series. So I take the linear combination where I cancel the constant terms. So this thing has constant term theta s, and this thing has constant term theta r. So I multiply this one by theta r and this one by theta s, and I subtract, and I get constant term 0, as long as the other stuff that's in the formula is constant term 1. Okay? So basically, I want this vk to just go away. So I want it to be 1 mod p to the m. So m is some high power of p that you're trying to get congruences for. So I want this to basically go away. And Hita proved that such a form exists, that there's a form whose Q expansion is just 1 mod p to the m. And so this is a little bit more subtle. So this is a group ring modular form that I want for just this character, not with the chi, that's congruent to 1 modulo p to the m and the augmentation ideal. And I want both to have constant term 1. So the truth is, I don't know how to define this or whether it should even exist. So I should say that when I say this is not yet a theorem, the problem is constructing this. If I knew how to construct this, I'd be pretty confident that we could say that this would be a theorem at this point. But we have a trick to get around this, but we have to check all the details there. Okay? So the point of this, so why do I want this to be 1 mod I? Because then this is an I, so then the whole thing mod I squared, I can make it go away. Okay? Because if this is 1 mod I and I multiply it by I, then by something in I, then it's congruent to that something modulo I squared. So then this kind of goes away, and this goes away by construction. So then I get something that just looks like a difference of 2 Eisenstein series. So mod I squared is Eisenstein. Okay? So the key point is it's Eisenstein for all the Heck operators for which these have the same Heck eigenvalues, and those are all those away from p, mod I squared at least. And then at p, they have different Heck eigenvalues, and if you calculate the action of up on this thing, you get basically the ratio between theta s and theta r. And that's how the theta s and theta r show up. Okay? And then, as I said, the derivative of the up operator is related to the Galois representation from the theorem of Hita. So that's how the theta s over theta r gets related to something in the Galois representation, which is your cohomology class, which gives you your proof of the theorem. OK, that's it. OK, so part 2 tomorrow will be details. All right, thank you.